Welcome to Daily Papers, the podcast where we break down fascinating research into bite-sized conversations. Today, we're diving into the quest for the holy grail of artificial intelligence, AGI.
Right, AGI, or Artificial General Intelligence. This isn't the AI that suggests your next movie or beats you at chess. This is the big one, an AI with human-like intelligence that can learn, reason, and adapt across a huge range of different tasks.
The problem is, while everyone in tech is racing to build it, there's no single agreed-upon blueprint. We have dozens of different approaches, like reinforcement learning, schema-based learning, and causal AI. It's like everyone is trying to build a new kind of vehicle, but nobody can agree on what a vehicle even is, let alone how to compare a car to a boat.
Exactly. And that's where today's paper comes in. It's titled Towards a Category-theoretic Comparative Framework for Artificial General Intelligence. It doesn't try to build an AGI, but instead it proposes something arguably more important right now, a universal translator, a way to create a common mathematical language to describe and compare all these different AGI designs.
Okay, category-theoretic sounds a little intimidating. Can we break that down?
Absolutely. Think of category theory as the mathematics of structure. If regular math is about the numbers, category theory is about the relationships between things. It's less about individual Lego bricks and more about the rules for how they can connect. It lets you draw diagrams, blueprints really, that show how a system is put together and how information flows through it.
So it's about creating a blueprint for an AI. The paper makes a really important distinction here between the architecture, the blueprint, and the specific AI agent.
Yes, and they use a great analogy, a car assembly line. The architecture is the sequence of stations. First the chassis, then the engine, then the wheels. It's the overall workflow. A specific implementation would be whether a human or a robot is tightening the bolts at one of those stations. This paper is only interested in the blueprint, the architecture itself.
And it says these blueprints have two key dimensions. First is the syntactic structure, which is that assembly line workflow, how information flows from perception to action.
And the second is the epistemic structure, which is all about knowledge. What kind of knowledge can the AI store, and how can it change that knowledge? For example, can it only update existing beliefs, or can it create entirely new concepts from scratch? Two AIs could have the same workflow, but handle knowledge in completely different ways.
This is where the framework gets really powerful. It lets us draw the blueprints for different AI approaches and see exactly how they differ. The paper walks us through a few examples, starting with a classic, reinforcement learning, or RL.
Right. In this new blueprint language, the architecture for reinforcement learning is very simple. All of its knowledge, everything it has ever learned, is basically stored in one single massive blob of data. You can think of it as a giant, undifferentiated to-do list for every possible situation.
The workflow is simple. The AI sees the world, consults its giant knowledge blob, takes an action, sees what happens, and then tweaks the blob a little bit. It's effective, but the paper calls this an informational bottleneck. Everything has to be crammed into that one place.
So, the next step up is an architecture called causal reinforcement learning, or CRL. This blueprint is more sophisticated. It splits that one big knowledge blob into two. One part is for the policy, that's the what to do knowledge. The other is a causal model of the world. That's the how the world works knowledge.
And that's a huge improvement. Now the AI can separate its strategy from its understanding of physics or cause and effect. It can ask what-if questions without having to actually try something and risk a mistake. The blueprint clearly shows there are now two distinct feedback loops for learning.
But the paper takes it one step further with the final example, schema-based learning, or SBL. This architecture is a whole different ballgame. Instead of one big messy document, knowledge is broken down into a whole collection of small, modular, reusable tools called schemas.
It's like going from one giant messy document to having a phone full of apps. You might have a recognize a cat schema, a pick up a cup schema, and a navigate a room schema, and you can combine them, update one without breaking the others, and even create new ones.
Exactly. This modular design is much closer to how we think cognition might work. It allows for continual learning, where an AI can learn new things without catastrophically forgetting everything it knew before, which is a massive problem in AI today.
So, by using this category theory framework, we can clearly see the evolution. We go from reinforcement learning's single blob to causal RL's two distinct blobs, all the way to schema-based learning's library of modular tools.
It's not just a new algorithm, it's a fundamental change in the architectural blueprint. And that's the whole point. This framework gives researchers a precise way to talk about these differences. It allows them to compare designs on an equal footing, to see where the real innovations are, and to map out what features are needed to get closer to true AGI.
So, this paper isn't the final answer to creating general intelligence, but it's providing the engineering principles and the drafting tools needed to design it. It's laying a rigorous mathematical foundation for what has been, until now, a bit of a chaotic gold rush.
It's a crucial step in moving the search for AGI from an art to a science, and that's a pretty big deal. That's all the time we have for today. Thanks for tuning in to Daily Papers.